Hi, this is Barrett Givens. In this video, we're going to introduce the definition of a continuous function in topology and then do some simple examples. All right, so here is the definition. Let x and y be topological spaces. A function f from x to y is continuous if the pre-image of any open set in y is open in x. Another way to say that is f is continuous if and only if, whenever u is open in y, the pre-image of u is open in x. All right, so let's go ahead and do a simple example. So here I have an example. I have two topological spaces. They're both these finite topological spaces. So x is the space ABC. And I've pictured the topology on X by circling the open sets here, okay? So the topology on X would include the empty set, singleton A, AB, and ABC. And then Y is the set 1, 2, 3, and the open sets in Y are just the empty set, the set containing 2, and then the set containing 1, 2, 3. And I have three functions listed to the side over here, and I'd like to know which of these three functions are continuous. And notice that f, the first function there goes from x to y, and the second function goes from x to y. The third function h actually goes from y back to x. Okay, so maybe if I'd been really smart, I would have used lowercase y's over here. Let me do that just to make it more clear. Y and h of y. Okay, so let's look at these and try to figure out which ones are continuous. So the definition of continuity says that you have to look at open sets in your codomain. So let's start with the function f here. F takes a to 1, b to 2, and c to 3. And I want to look at open sets in my codomain. So I want to start out by looking at open sets here in my codomain and then thinking about their inverse image. This example is fairly simple because there's only 3 open sets here. Okay, so there's only 3 open sets here. The only open sets in the codomain here are empty set, singleton 2, and 1, 2, 3. So we just have to check each one of those. And the empty set, we don't really ever have to check because the pre-image of the empty set is always the empty set. So the empty set is open and its pre-image is always open. You're never going to have to think about the empty set when you're thinking about the definition of continuity. So let's just think about singleton 2 and then the set 1, 2, 3. So under F, the pre-image of 1, 2, 3 is ABC, which is also open. So that one's fine. But the pre-image of singleton 2, what is the pre-image of singleton 2? So if I look at the definition of F, which inputs give me an output of 2? Well, just B. And B is not open in the domain. And so F inverse of singleton 2 is singleton B. And this is open, singleton 2 is open, but singleton B is not open. So if you can find one example like then that tells me F is not continuous. Not continuous. Okay, so F is not continuous. What about G? So for G, again, I just have 3 open sets in my codomain to think about. The empty set, I don't really have to think about because the pre-image of the empty set is always the empty set, so that's going to be easy. The pre-image of 2 here, for G, the pre-image of 2 is A. So G inverse of singleton 2 is singleton A. And over here, singleton A is open. So this is an open set, and its pre-image is also open. What about the pre-image of 1, 2, 3? Well, that's ABC, which is also open. So there's 2 open sets to check in my codomain, and the inverse image of both open sets is open, and so G is continuous. Okay, now what about H? H goes in the opposite direction. H goes from Y to X, okay? So again, I have to look at the pre-image of open sets. So what are some open sets in X? We're going to start with the codomain for H, which is X. So let's start with singleton A. Singleton A here is singleton 2. So singleton A is open. Its preimage is singleton 2, which is also open. Okay, what about AB? AB is open over here. So AB, the preimage of AB is 1, 2. That's not open here. So I have an example here. So H inverse of AB is 1, 2. This is open. This is not open. And so therefore H is not continuous. All right. So hopefully that helped a little bit with just understanding the definition of continuity. Now, in real life, we're probably not going to mainly want to use this definition on examples like this, where you just have three elements. It's not clear exactly what that means in this kind of situation. But the idea is that to check that a function is continuous, you have to think about all possible open sets. And you have to check that for every possible open set, the preimage is also open. And usually, I mean, here we just did it by listing all of the open sets and then like checking them one by one, but usually it might be more something like we have some kind of standard format that all the open sets take. Like maybe they look like open intervals, or they look like unions of open intervals, or they look like sets with finite complements or something like that. So we just take a generic set of the right type and we look at its preimage. To show that a function is not continuous, you just have to find one example of an open set whose preimage is not open. And so that's going to be the same when we're in more complicated topological spaces. The idea is that to show a function is not continuous, you just need one example of an open set whose preimage is not open. All right, thanks for listening.